Okay, now we're having the next talk by Hai about optimal community structure. The stage is yours.
Hello, everyone. I'm very happy to be here. Actually, I'm from another domain, basically focusing on constraint programming. And this one is a side project. In this project, we also use a little bit MaxSAT-based proof login solving. And from the user perspective, here most of the guys are the experts of proof login itself, and maybe we can also get more insights from you guys. Due to the collaboration with Carlos, Fadiana, and Stefan, then we get these projects done last year, and we also had a lot of follow-up issues. Here is motivation for us. Basically, in the physics domain, modularity problem is a quite famous problem, and to understand graph-based scenario, they always want to partition the graph into different groups, and then regarding different groups, we can get a metric which can be used for the identification of the quality of the clustering. So with the clustering, also high quality clusterings, we can get very good analysis regarding a lot of real world applications. So here is a background, and we just want to get a very good clusterings for their graphs, and then we just want to use SAT solving. Here is a modified version of MaxSAT solving. We call it MaxSAT solving to solve these problems in an exact way. And in this domain, there is always a debating between the optimality and the computationability, which means there are also a bunch of heuristic algorithms in this domain. But if you want to prove the optimality of the solution, then it's also an NP-hard problem. So a lot of papers, I mean, in the last several years, they're claiming, okay, heuristics can always fail to get the optimal solutions. But initially, when you step into this domain, we also think, okay, now let's agree with it. But after we did several months for the application problem, we also found, okay, for our heuristic algorithms, because our heuristic algorithms are based on a heuristic solution generated by another algorithm. Based on this solution, we could never get improved results. And then we are considering probably in this domain, the tendency is a little incorrect, which means some heuristics can always get optimal solutions, even they cannot prove the optimality. And that's our standing point. So we just want to verify whether it's true or not, whether the heuristic methods can always get optimal solutions. And here is our answering solutions. But our solution landscape will also cover a lot of different scenarios, from heuristic methods to exact methods, which can get optimality, guaranteed solution. Afterwards, we also do the proof login for the MaxSAT solving to further verifying the optimality of the solutions among the problems. In case anyone not so familiar with the domain, I also give some preliminaries for this problem. Basically, this one is also originated from the physics domain, and give a partition of the graph. I mean, as long as you give the partition of the graph, partition the different nodes into different groups, and then we can calculate a Q value for the partition, and then we can get this value. We call it modularity value. Usually, this value can evaluate the quality of the partitions. I don't explain it in detail regarding the definitions, but you can see it gets a lot of attention in this domain. Usually each year there will be over 1,000 citations. And here I also give an example. Here is a simple graph. And when you partition the graph into two groups, and then, for example, node 1 and node 2 are in the same graph, node 3 and node 4 are in the same graph, and then we can get the two communities, and then we can calculate the modularity values according to the definitions I showed just now. Here is also another side of the solving landscape, which means we use MaxSAT solving. It's basically an optimization version of MaxSAT solving, but in the original SAT solving, we only have one kind of clauses, which means we have to satisfy all the clauses in the formula. But here we also have soft clauses, which means we want to satisfy all clauses in the all hard clauses. In the meantime, we also want to maximize the number of satisfied soft clauses. Of course, you can also add different weights into the soft clauses. Then we can get a max value of the problem, which means objective values. That's what we want in the optimization problem. And here is an example. For example, we also have two clauses, hard clauses, and we also can assign different weights to the soft clauses. And the goal is what I said just now. For example, if we get the assignments like 101 for the 3 variables, then all the soft clauses can get the max value of the weights. And in the meantime, we also can guarantee the satisfiability for hard clauses. And here is our basic framework using MaxSAT solving for the modularity problem. Now it's encoding. Basically, the encoding is quite simple. We just use the transitivity encoding. Of course, before realize that we also do a lot of other tentative trials for different encodings, like lazy encoding, like given the specific number of partitions, we then do the encodings. Here, we set the hard clauses, use transitivity. If U and V and V and W are in the same partition, basically we can imply U and W in the same graph. And for soft clauses, we also transform into a gain information. Gain information basically is a number of edges in the because here we have to make the weights into a natural value, which means we have to do some transformations. But here you can just basically regard it as a number of edges enter the partitions, and then you can use this one as an indicator to show the information gain. But I don't talk the details here because there are a lot of transformations for the equations. And here you can just regard it our objective as the maximum number of the weights where we can satisfy all hard clauses. And we also get another modified version of the encodings I mentioned just now, because usually if you get the full encoding of the problem is quite large, even sometimes it's quite difficult to read the encodings for the MaxSAT solving. So we also propose a sparse encoding, which means we can introduce a separator which can reduce a lot of transitivity clauses. Here we have to calculate the separator for each node, for each pair of nodes U and K. Basically, this separator is a any of the cut set of the graph, which means after you remove the set in the graph, and then U and V is not connected anymore. And of course, we can also guarantee the same optimal solutions as full encoding. And here is our theoretical guarantees. I won't prove here because it's more messy. And then basically we can guarantee the same modularity with the two encodings. And of course we can get the optimal solutions in the same way, but we can also guarantee the equivalence for the two encodings. And here is our experimental results for the different encodings and during the MaxSAT solving. Because as I discussed just now, for heuristic solutions, there are a lot of surveys they claiming, okay, for most of heuristics, they cannot get the optimal solutions, but here is the statistics from their side. But after we investigated a lot, then we found probably it's not true. And we also include more heuristic methods. And we also found a previous heuristic method called Vienna cluster is always getting better results. And based on the heuristic solutions, we also did a lot of improvements, but we failed to improve it. Then we realized it, okay, probably is already optimal solutions. That's the reason why we couldn't improve it. So we have to verify it. And of course, the heuristic solutions are always computed quite fast. And we also extended to much larger instances. Here is a number of nodes and a number of edges in the graphs. And here we also tried almost all the existing so-called best MaxSAT solvers. But finally, we choose MaxHAs because it always can get best results. And on all these kind of instances, we can get optimal solutions. Of course, regarding the previous version, they can always get on the blue points, which means the smaller number of instances, but we can extend it into another scale. And we also did a comparison between full encoding and sparse encoding in two dimensionalities. The first one is the solving time. The scales are log scaled. And for each instance, we tried both encodings and we can find, okay, for almost all the, I mean, not all, but most of the instances, we can get a large scale of speeding up. And for the size of encodings, we can also improve a lot. Basically, we can get dominant better results than the full encodings. And of course, we also compare the exact solving, by which we can get optimal solutions. But for heuristic algorithms, they can always get faster because you can see it's always less than 10 seconds. They can already get a better result. I mean, get the same good results, even it's not verified. But with our MaxSAT solving encodings, we can get it verified. It's truly optimal solutions. And to verify it, here, of course, there are some notes because for heuristic solutions, it's difficult to get multiple optimals because for some partitions is isomorphic. So basically, they cannot get all solutions in one shot, but with MaxSAT solving, we can get it. Here, we also use the certifiable MaxSAT solving. The whole pipeline is by Pacos and VariPB checker. Initially, we want to try all more MaxSAT solvers which can be verified, but unluckily, for all these kind of solvers, we couldn't get any instances verified because due to the large scale of output logs, and of course, the solving time is also much longer than the MaxSAT solvers we mentioned, like MaxHS, even though it's not proof verifiable. Here, initially, we have a lot of problems, but we also did some engineering modification. We did we compress the log during the solving, and then we can also get a lot of speeding up. I mean, not only regarding the speeding up, of course, we can also get shorter, a smaller running time than the proof logs are also smaller, on which we can verify it by veripeating. But interestingly, we also do the comparison between the two encodings on the previous setting of exact solving for MaxSAT solvers. We can always get better solutions. I mean, better efficiency for the sparse encoding. But here, for the verifiable MaxSAT solving, the sparse encoding and the full encoding are basically similar. So we didn't get any gains from the sparse encodings. And you can see the solving time is always similar for sparse and full. And for the proof log size, it's also similar. And on more than 100 instances, we can only get around 36 instances solved. Of course, we can also verify it. And here is our summary. Basically, we get a full landscape for the confidence and the efficiency for this famous problem in the physics domain. And we have a full tool chain. If you want to get the solution very fast, we can use just heuristic solutions, heuristic methods, which cannot guarantee the optimality, but according to the experiments we have done, is always the best optimal solutions. Of course, if you want to get higher confidence, you can also get the MaxSAT encodings, of course, including 2 versions. And for the sparse encoding, we can also get speeding up for the on the basis of full encodings. And if you want to get a higher verification, then we can just use MaxSAT solving for proof logging. But it's really high cost. So basically, we answer the questions I requested just now. In this domain, the previous investigation seems to be not systematic, and there are a lot of overlooked insights. So we just build up a full landscape for this problem, and for the researchers in this domain, they can always get suitable algorithms for their different requirements. And for here, it's also quite an interesting insight that MaxSAT encoding sometimes it can get faster for normal MaxSAT solvers, but for provable MaxSAT solving, it's not guaranteed. For example, here the sparse encoding incur no benefits. Even the MaxSAT solving with the proof logging can get highest confidence. And for the future work, we also want to investigate this phenomenon. And of course, we also want to scale up more advanced MaxSAT solving in the proof logging syntax. And of course, now with Carlos, we also have a new MaxSAT solvers which can get more instances verified, and using another refreshed way. Maybe it's our follow-up work. And in the meantime, probably in the future, we can also integrating some tuning techniques into the real application domain. because sometimes if you get a lot of parameters, a lot of configurations in this solvers, it's also quite difficult to guarantee the efficiency. Even you can verify the efficiency on the benchmark problems, but for real application problems, it's not so easy to get desirable results. Here is our full landscape of the solution, and I'm not sure whether the time is already long enough.
Still have time, but if you haven't, don't force yourself to say something.
Okay.
If you are done, you are done.
Okay, my talk is done because I'm basically from a user perspective to talk to what we have done in this project.
Sorry, I think I missed it, but what did you do for compression? Because you just said, right? Maybe I just missed it in what you said. Right? So, because there are several things you can do for compression, right? You can just try to produce shorter files in the sense of having binary file, let's say, which is like the SAT competition, or you can just compress it with XC or something.
No, we just hack into the parcels and we will transform, doing some online streaming compression for the logs, not output it directly to the disk. Then it's so huge. We even
only a factor 6.
Yes. But it's just a case study for the problem. We didn't try it for longer running time and.
Okay, it's just because I've seen CNF files going from over 100 gigabyte down to 5.
It's so huge. It's
down to 5, right? So factor 20. So you getting only a factor 6 out is a bit surprising. But okay.
Sometimes when you are really using the verifiable MaxSAT solving, it's also a pain because initially we thought, okay, at least we can get several instances verified, but when we apply it, we only get several instances, which somehow is disappointing. And then we have to hack into the solvers by ourselves and just try to get better efficiency for the proof logging. And we even try some other techniques, like we do it in an online way, which means during the we don't output it. We call the verify PB in the meantime when we get the logs.
So
during the running.
You pipe it to already.
Yes. Yes. So basically we have 2 threads. It's like one thread from the MaxSAT solving is feeding some information to the PB.
Is PB fast enough?
No. I mean
to consume the output. Because I know for SAT solving we do this also, and here it's just the checker is faster than the solver producing.
Here the checker is quite faster. I mean, in our context, they are only less than maybe 10% time consumption by checker, which means it's tolerable.
Yeah, but the question is whether it's not blocking. Because when you use a pipe, you have the pipe has a certain size, and when the pipe is full and the producer is waiting, right? Then you have to stop.
Yes, that's true. But we didn't count the waiting time. We just count the processing time for the checker. You know what I mean? When the pipe is full and then the checker began to run, and then it's counting now. It's counting time now.
Yeah.
And when the pipe is empty, then we stop it.
Yeah, true, but on the solver side, I mean, on the solver side, also taking time, right?
Yeah, that's true, because sometimes
you probably want to avoid having a burst where the solver is able to produce very fast a lot of proofs and then it has to wait.
Yes.
Very naive question. Could you come back to slide 23 where you have
23.
So basically you have a ladder, right? So you have the fast not proof method, and then you can go to full proofs. Can't you use this? I mean, can't you use hints to climb the ladder? So starting with very fast, no guarantee, and then getting some information out of it to go faster for the next stage, and etc. etc.
Yes, actually, our original project idea is because there are already a lot of heuristic algorithms. So in our another project we called set-based local improvement methods. We call it SLIM, which means every time you give a heuristic solution to the set solving, we will just based on this heuristic solution dig out a local part from the solution, and then this problem is smaller, and then no matter what kind of encodings we get, even is cubic or quadratic, then we won't get a huge explosion for the encodings. Then we can improve it iteratively. But the problem is that regarding the Vienna cluster, we want to improve it, but we failed. Then we realized, okay, it's not possible to do like this, because for the best heuristic methods, they can always get the optimal solutions, even if it's not verifiable. But of course, if the solution is not good enough, we can also add some assumptions to the set solving. Also, like to our MaxSAT solving, we can also add assumptions. Okay, maybe regarding the assumptions, you can do some searching based on the solutions generated by heuristic algorithms.
Even for proofs, I mean, in automated reasoning, sometimes you use a very fast solver that does not produce proofs and gets information from it.
Yes.
And use it to produce proof with a smaller, slower solver. So that's what to do. So maybe also at this stage. I don't know.
Yeah, it's also possible.
Can you give a hint to the MaxSAT solver? So like you get from your initial heuristic, you get the solver, and then you tell the MaxSAT solver, okay, I found an optimum value, just try this one out.
You mean the hint by MaxSAT solving?
No, you get the hint from the V-clues. I mean, you get from the heuristic, you get the initial value, and then you give it to the MaxSAT solver, says this works. Now try to prove that this is the optimal value.
We didn't try it like this, actually.
I mean, I'm not sure MaxSAT solver support it, but on the other hand, if you're hacking MaxSAT solvers anyway, you probably can just also add this.
Because initially we were also considering to use incremental MaxSAT solving, but we didn't get a lot of applicable, usable, high efficient.
How's EPAMIR, right? EPAMIR interface.
Yes, but
any solver that supports it?
No.
Okay.
Actually, we also tried lazy encodings. We didn't get promising results. So we also tried a lot of other paradigms.
I mean, the extreme case you could do is if you know what the optimal value is, you can just call a SAT solver.
Yes, but
just to try okay, it's worse because you have to encode it, but you could just say, well, if it's unsat, then you know that it was the optimal solution. If you just want to prove that something is optimal.
Yes, but in the meantime, we were, for example, on the case, previously we have no idea whether it's optimal or not. It's just our guess, and then follow this step. Okay, after we verify for a long time, for example, 2 days for each instance, then we notice, okay, it's already optimal. But previously, no one gets the idea. So afterwards, of course, we can claim it.
Yeah,
we can do. And I'm also a little bit curious why the PACOs cannot get any benefits from the sparse encodings. Because for normal MaxSAT solvers, it can always get better results almost.
Probably. What do you call a normal SAT? What you use MaxHS, right?
I also try a lot of benchmark.
Yeah, but what I mean is Percosa is the only MaxSAT solver based on this SAT approach, on the CDCN approach, right? I mean, it's all the others are doing something completely different. So maybe you're observing benefits on all the others because it works for their approach, but Percosa is using a different approach.
Yeah, I know what you mean. Sometimes for normal best performing MaxSAT solvers, they always get SIPs or other MIPS solvers inside of the core calculation.
But I'm not a MaxSAT expert. I leave this usually to my colleague Andre.
I have a question about the encoding for the one of the very beginning slides where you defined this Q of P. That had a quadratic term, and that was the value you wanted to optimize, right?
Yes.
And for the encoding, you have linear weights for the individual clauses that represent that one node is part of the one partition or the other.
Mm-hmm. No, we just consider the pairs. Do you mean the sparse encoding or full encoding?
I think in both you had it.
Yes, but we only consider the separators for the sparse encoding. That's the reason why we can get fewer pairs of UV, which we will consider for the soft clauses.
Okay, so from the pair you get this quadratic term because you're considering two nodes at once by looking at the edge. Okay, okay, that makes sense. Thank you.
I have a last dumb question. Why is the timeout 48 hours? Just because you cannot get more
yes,
from the cluster?
Yes.
Or did you experiment with this? Or what?
We try because it's like for example, in the first batch of the experiments, we just try 50 instances. Then we just want to play around for more variants, and then we extend it to more instances for longer timeouts. But of course, we also want to compare the MaxSAT solving with MIPS solvers. Actually, I didn't show the results here. We also compare the MaxSAT solving with Peruvian and Cplex. In the previous paper, they claiming they can get what kind of results within 2 days. Then we can also compare our results in a fair way. Yeah. That's the main motivation.
Thank you.
Okay, then let's thank the speaker again.